In this video, I will go through 3 examples which will illustrate how to calculate the information content of a message. Now, I will assume that you've looked at the lecture notes and that you attended lecture, as always. And here are the lecture notes on my website. We're going to be using 2 formulas: calculating the uncertainty, which is a function of the probabilities that are attached to the states. So this will give you the uncertainty regarding which state the variable that you care about will be in the future from the user's perspective. And then below that, this log base 2, we can use this identity right here to actually calculate it on the calculator. Use the fact that log base 2 of a number is equal to the natural logarithm of that number divided by the natural logarithm of 2. The natural logarithm is on your calculator. Log base 2 is not on your calculator. And then finally, once we've calculated the uncertainty using equation 1, we can calculate the information content of the message using equation 2. If uncertainty increased or didn't change, then we say there was no information in the message. But if the message led to the uncertainty decreasing, such that the uncertainty after receiving the message is less than the uncertainty before receiving the message, then we say that there was information content in the message, and this is how we calculate it. This actually represents it's not the raw information content, but it's the percentage decrease in uncertainty regarding which state that J will assume in the future as a result of receiving and processing the knowledge contained in message M. J is just the variable of interest. We labeled it as J throughout the lecture notes. So we'll stay consistent with our notation. So let's start with the first example here. Excuse me. So example 1. Example 1 will just be a relatively simple example to illustrate the concepts. So let's let the variable of interest, call it J, we'll let it be the weather tomorrow. Now in all these problems, we're going to have a variable of interest, we're going to have a state probability distribution, and we're going to have a message. And these 3 things, using these 3 things, we can calculate the information content of the message. So the first thing is we need a set of states. So we know that this variable theoretically could take on one of infinitely many states. The weather is a continuous variable, obviously, but humans are inherently limited in their cognitive processing ability, and so they likely do not think of the weather as being in one of infinitely many states, but they rather partition this continuous state set into a discrete state set just to enable them to think about it, be able to comprehend it better, right? So let's suppose that they feel that the weather could either be rainy or sunny. So this is a discrete set, 2 states, n is equal to 2, n is the number of states. In this case it's 2. This will be little s1, this will be little s2. And then before they receive a message, their initial probabilities, or their initial state probability distribution, let's suppose that so before they receive a message, they feel that the weather tomorrow will be rainy with a 50% chance or sunny with a 50% chance. So these are the probabilities. We labeled them alpha in the lecture notes. This is alpha 1, this is alpha 2. So right away you can see that this individual is the most uncertain regarding which state the weather will be in tomorrow. You can't be, this state probability distribution represents the highest level of uncertainty. If each state is equally likely from the individual's perspective, then from their perspective they are the most uncertain regarding which state the weather will be in tomorrow. if you remember from lecture notes. Max uncertainty occurs when the probability of the ith state is equal to 1 over n for every state. Alright. In this case, there are two states, and alpha sub I equals 1 over 2 for each I, for I equals 1 and I equals 2. So when that happens, the individual is the most uncertain. Now we could show this, we could show theoretically that the uncertainty the measure of uncertainty that we're using is this measure right here. We could show mathematically using calculus and the method of Lagrange multipliers, we could maximize this function subject to the constraint that the probabilities have to sum to 1. The sum of the probabilities, the sum of the state probabilities has to equal 1. So if we maximize this function subject to that constraint using the method of Lagrange multipliers, which is I believe a concept from calculus 2 or 3, then you would find that the alpha is the choice variable here. You're trying to find alpha that maximizes it, and you will find that alpha sub I has to equal 1 over n for all I at the maximum level of uncertainty. So intuitively you can see that has to be true, but actually mathematically we could show that intuition really does work in this case. So that's that. Now let's let them receive a message, and the message will just be a weather forecast. So they're sitting there today. Before the weather forecast, they feel that the probability of the weather tomorrow will be sunny or rainy is 50%. Then tonight, they get a weather forecast. After the weather forecast, they update their probability distribution accordingly. So P sub A represents the probabilities that they assign to the states after the message. P sub I represents the probabilities that they assign to the states before receiving the message, or initially. Let's suppose they update it like this. So something the weather forecaster said, maybe the weather forecaster said that he thinks that there's a 60% or a 40% chance of rain tomorrow, and therefore they thought that leaves 60% chance for sun. So now, theoretically, when we set this up, we make it to where the states are discrete and they are exhaustive. So there is no state that the weather could be in tomorrow other than these two states. And they don't overlap. So the weather can't be both rainy and sunny at the same time. It can't be both rainy and sunny tomorrow. That might not quite fit, right? The weather could start out rainy and then turn sunny. But let's abstract away from that. And in the theory, in the setup, in the lecture notes, the states are exhaustive. They exhaust the state space. The variable of interest cannot be in any state that's not in the state set here. And the states are non-overlapping, mutually exclusive. So this might not be the best real-world example to fit that theory, but it's an example. All right, so what we want to do now, the end result, what we want at the end is we want to calculate the information content of the weather forecast. If the forecast changed their probabilities on the states from this to this, what was the information contained in the forecast? First of all, was there information contained? Well, we can see that uncertainty must have decreased. If you can't get it any more uncertain than these probabilities, then these probabilities down here are some different probabilities than these, and you can't get more uncertain than these, so these probabilities must represent a lower level of uncertainty, or a higher level of certainty, if you want to say it like that. So uncertainty is decreased. If you look in the lecture notes, the formula for the information content of a message, there are two cases, right? Either uncertainty decreased, in which case there is information in the message, and we can calculate it using this, or uncertainty did not decrease. It either stayed the same or it increased. in which case there is no information in the message. No information in the sense that we do not learn anything about which state, we don't become less uncertain regarding which state the weather will be in tomorrow. And we define that as no information. Alright, so what we want to do is we want to calculate the uncertainty of the initial state probability distribution. And the reason we write it like this is the uncertainty of the initial state probability distribution is a function of the probabilities. It's not that we're uncertain in these probabilities. No, we're very certain initially. These are the probabilities that we attach. It's not that we feel the weather will be rainy tomorrow with a 50% chance, but we're 40% certain about that probability and 60% not certain. It's not like that. We're not calculating the uncertainty in the probabilities. We're calculating the uncertainty regarding which state the weather will be in tomorrow. And it's a function of the probabilities. So that's why we write it in this way. But we're not uncertain in these probabilities. Alright, so we have, let's see, we can go ahead and use the formula, right? Formula 1. This measure that was derived by Claude Shannon in 1948 in his paper, A Mathematical Theory of Communication, which we talked about in lecture. The alphas are the probabilities, obviously, and n is the number of states, so we can just, we have to put a negative sign in front of it. Don't forget that. We'll talk about that in a second. So this is what we're calculating. But the thing is, we can't calculate log base 2 on our calculator. So let's use this identity that we gave in the lecture notes. Log base 2 of any number is exactly the same thing as the natural logarithm of that number divided by the natural logarithm of 2. So let's just substitute that in right here. Log base 2 of alpha sub I is exactly the same thing as the natural logarithm of alpha sub I divided by the natural logarithm of 2. So there we have that. Now, you'll see why we're going to put the negative sign here in a second. Why is people usually, whenever they see this for the first time, they wonder what's this negative sign for? But let's keep that out there. Now put in 1 for I. So we're going to have alpha 1 times the natural logarithm of alpha 1 divided by the natural logarithm of 2. And then a plus sign because we have a summation. Then put I equals 2 in. So alpha sub 2 times the natural logarithm of alpha sub 2 over the natural logarithm of 2. So this is what we're calculating. And now we can substitute in for the alpha sub 1 and the alpha sub 2. So we're going to have negative. And notice we can pull out a 1 divided by natural logarithm of 2 out, because that's common to this part and this part. 1 over ln 2 is common, so we can just pull that out. Pull that out, and then what do we have? We have alpha sub 1 times the natural logarithm of alpha sub 1. Well, alpha sub 1, a probability on the first state, the probability of it being rainy, the probability of state 1 is 0.5. Probability of state 2, alpha sub 2, is 0.5. So we're going to have 0.5 times natural logarithm 0.5 plus 0.5 times natural logarithm 0.5. Alright, so we have negative 1 over natural logarithm of 2, and then 0.5 times natural logarithm 0.5 plus 0.5 times natural logarithm of 0.5. Well, that's just 2 times 0.5 times the natural logarithm of 0.5. And 2 times 0.5 is just 1, so we're just going to have 1 times natural logarithm 0.5 left over. And now you see the reason for the negative sign. The natural logarithm of any number between 0 and 1 is a negative number. In fact, You might recall from grade school, if we graph x versus the natural logarithm of x, the function looks like this. When x is equal to 1, the natural logarithm of 1 is 0. For any values x bigger than 1, so everything over here, the natural logarithm of x is a positive number, right, because it's north of the x-axis. And for any value of x less than 1, so all the values here, the natural logarithm of x is a negative number. All probabilities are between 0 and 1, so they're definitely less than 1 and bigger than 0. So the natural logarithm of any probability is a negative number. If we don't put the negative inside right here, then our final answer for the uncertainty is going to be negative. And it doesn't make sense to have negative uncertainty. So that's the reason why there's a negative sign. Alright, so we can calculate in our calculator. And I'll do that real quickly, if I can find my calculator. So we have ln of 0.5, which is negative 0.693147 and so forth, multiplied by, or divided by, if you want to do that, divided by negative natural logarithm of 2. And you get the answer 1. And the units of uncertainty, which I don't think I talked about in the lecture notes, but I'll have to go back and add that. But the units of uncertainty are bits. 1 bit. So it was Claude Shannon who coined the term bit. And you know that 8 bits equals 1 byte, and so forth, right? So this idea of bits and bytes and megabytes and kilobytes and gigabytes originated with Claude Shannon. Right. Then we calculate the uncertainty of the ex post state probability distribution, and we will find that it's smaller than 1, which is good. So we can go ahead and take out the 1 over ln 2. We can always just take that out, actually. And on the inside, we're going to have, now, our probabilities after receiving the message were 0.4 and 0.6. So this is what, right, we put I equals 1 in. That would be 0.4 times natural logarithm 0.4. Of course, divided by natural logarithm of 2, but we pulled that out. And then we put I equals 2 in, and you would get 0.6 times natural logarithm 0.6. This is the multiplication sign here. All right. And then we calculate in our calculator. And you will get 0.97095. I'll just take it to 2 decimal places. Let's just do that to keep it simple. So you can see that uncertainty went down, which makes sense. You might think that uncertainty would go down more if you went from 0.5 into 0.4, you might think it would go down more, but it doesn't actually. And so the information content of this message, well, first we would make sure that the uncertainty after is less than the uncertainty before. Make sure of that, because if that's not true, then we can't use, see, equation 2 is there are two scenarios, right? If this is true, then this is the information content of the message. But otherwise, 0. So since that's true, then the information content of the message is the absolute value of the decrease divided by the maximum amount it could have decreased by, right? And the most it could decrease by, the most uncertainty could decrease by as a result of getting a message is just whatever the initial uncertainty you started with. You get rid of all of your uncertainty, but you can't get rid of any more uncertainty than you originally started with. So this calculates intuitively this calculates the percentage decrease in uncertainty. So we're doing 1 minus 0.97, which if uncertainty decreased, this will always be a positive number. There's no need to take the absolute value. So I should change that in lecture notes as well. Divided by 1. And you can see that it's 0.03 or 3% information content. The message decreased our uncertainty by 3% of the maximum amount it could have possibly decreased it by. So of all the possible messages we could have gotten, the best message would have decreased it all the way down to 0. So we'd be completely certain regarding which state the variable of interest will be tomorrow, which state the weather will be in tomorrow. But we got a weather forecast that decreased our uncertainty only 3%. So that's the information content. So that's example 1. Let's go on and move to example 2. This one will be a little more involved because I won't actually give you the probabilities. You'll have to solve for them. And then once you've solved for them, calculating the information content of a message will be, you'll do the same procedure as we did in example 2. So let's set up this example. Suppose the user is possessed with the following knowledge initially. So we'll label it K sub I for the initial knowledge that they have. So they know that there's an urn that has 5 balls. That's a colon. Or, I'm sorry, a semicolon. That's not J, that's a semicolon. Maybe I'll put a colon so you don't get confused, because we're going to use the letter J to represent the variable that we care about in a second. 2 of these 5 balls are red. 3 of the 5 are white. So this is what they know initially. Oh, they also know another thing. They also know that 1 ball is drawn at a time from this urn, but without replacement, which means that the ball is drawn and it's set off to the side. It's not put back in the urn before another draw is made. Now, let's suppose that the variable of interest, the variable we care about, is we want to know the color of the ball that will be drawn on the second draw. Alright? That means our state set, so you can form the state set then. State set then would be what? Depends on the variable of interest. Remember, in the first example, the variable of interest was the weather tomorrow. Then I had to tell you what the state set would be, because you didn't know what states that they were considering the weather would be in. Maybe they would consider rainy, snowy, sunny, cloudy. all four of those states. But no, I said they considered it rainy. It's either going to be rainy or sunny from their perspective. Here, though, you can actually, it's not subjective. According to the knowledge that I gave you, that the user possesses initially, what is the state set if this is the variable of interest? What color could what color could the ball be that will be drawn in the second draw? There's only two possibilities, right? It's either going to be red or it's going to be white. We'll label it R2, W2 to represent it's either red on the second draw or white on the second draw. All right? Alright, so based on the knowledge that the user has initially, they reason that, so what we want to do is we want to attach probabilities, right? We want to give our initial probabilities before receiving a message. In other words, we want to know what's the probability that red will be drawn on the second draw, given our initial knowledge, right? Well, it depends on what was drawn on the first draw, which I didn't tell you about, right? If red is drawn on the first draw, then the probability that red will be drawn on the second draw would be 1/4, right? If there's been one draw and the ball was red, now there are 4 balls left in the urn. One is red, because one of them's already been taken out, and there were 2 red at the beginning. So there's 4 balls left after the first draw. 1 is red, and 3 are white. So there's a 1 in 4 chance that the second draw, the ball drawn, will be red, if red was drawn on the first draw. Remember, I told you these probabilities that we assign to the states, we know them with certainty. But it seems in this case, if you just look at it on its face, this example, if you just take a glance at it, it seems like these probabilities are not known with certainty because it depends on what was drawn on the first draw, right? Probability that red is drawn on the second draw, given our knowledge initially, would be equal to 2/4 if white was drawn on the first draw. So it seems that the probabilities that we attach to the state red drawn on the second draw, it seems like we're uncertain between either this one or this one, depending on what was drawn on the first draw. We're going to attach either the 1/4 probability or 2/4 probability to this state. It seems like we're uncertain, but actually, if you know a little bit about probability, you'll see that we're not uncertain. The idea is, here's the idea. If red is drawn on the second draw, so if the second state is realized, then either R1, R2 was realized. If red's drawn on the second draw, then either it was drawn on the first draw as well, or there was a white one drawn on the first draw. If given red is drawn on the second draw, given we're in this state, then we're either going to have this being the realization or this being the realization. Once we've had 2 draws, right? These are the only 2 possibilities that could have happened if red is drawn on the second draw. So what we can do, given our knowledge possessed initially, we can assess the probability of both of these events, right? And add them together to arrive at an assessment in a non-ambiguous assessment of this. Not this, 1/4 if this was drawn, or 2/4 if this was drawn. This is just what you would think if you just look at it on the surface, but that's not thinking about probabilities correctly. Alright? So, there's a product rule for probabilities. It should make sense to you. The probability that red is drawn on the second draw, given our knowledge that we know initially, is equal to the probability that this happened plus the probability that this happened. And this isn't the product rule. This is the this is just logic. That has to be true, right? Probability that red will be drawn on the second draw is the number of ways that red could be drawn on the second draw divided by the total number of ways that things could have happened, right? And that's exactly equal to these two probabilities added up, right? If red is drawn on the second draw, then either this happened or this happened. So the probability that red is drawn on the second draw is the sum of these two probabilities. Okay? Now we use the multiple applications of the product rule. This first probability, the probability of a joint event like this, it's a joint event, right? It's an event that happens sequentially. One part happens first, then the other part happens later, in time, sequentially in time. So it's equal to the probability that red is drawn on the first draw given our initial knowledge, multiplied by the probability that red is drawn on the second draw, given that red was drawn on the first draw and our initial knowledge. That's what this is equal to. Alright? And analogously, the second one is equal to the probability that white is drawn on the first draw, given our initial knowledge, only given our initial knowledge, multiplied by the probability that red is drawn on the second draw, given that white was drawn on the first draw and our initial knowledge. Let's move this over. This is the fact that this equals this and that this equals this. It comes straight from the product rule for probabilities, which is derived in freshman level probability class at the university. We won't derive the product rule for probabilities. But now it becomes easier because we know each of these probabilities. We're not ambiguous about any of these four probabilities. What's the probability that red is drawn on the first draw given our initial knowledge? Well, there are 5 balls and 2 of them are red. What's the probability that red's drawn on the second draw, given that red was drawn on the first draw in our initial knowledge? Well, there's 4 left. One is red, because a red was drawn on the first draw, and there were 2 initially. So one of them, if red was drawn on the first draw, then on the second draw, the probability that red will be drawn is 1/4. We've already calculated this actually earlier. Right here. Plus probability that white is drawn on the first draw, given our initial knowledge. Well, there's 3 white balls, 5 total balls, 3 of them are white. So for the first draw, there's a 3/5 chance that white will be drawn. And then the probability that red is drawn on the second draw, given that a white ball was drawn on the first draw. Well, again, there's 4 left, right? How many of them are white? I'm sorry, how many of them are red? 2 of them. So 2/4. And then, so this is 2/20 plus 6/20, 8/20, and that equals 2/5. So this is ironic, actually. This is interesting. The probability that red is drawn on the first draw given our initial knowledge is 2 over 5. The probability that red is drawn on the second draw, only given our initial knowledge, but not knowing what ball was drawn on the first draw, is also 2 over 5. In fact, you can show the probability that red is drawn on the third draw, given our initial knowledge, is equal to 2 over 5. The probability that red is drawn on the fourth draw, given our initial knowledge, is equal to 2 over 5. The probability that red is drawn on the fifth draw, given our initial knowledge, is equal to 2 over 5. If we don't know what happened for the first draw, then we're going to assign 2/5 probability that red will be drawn on any draw. For example, like right here, if we don't know what happened for the first 4 draws, the probability that red will be drawn on the fifth draw, given our initial knowledge, is 2/5. You can show using this product rule that we've done, you can show that it's that this holds. And this is what sometimes students really don't understand about probabilities. If you don't understand this, you don't truly understand probability. So anyway, there's the probability of the first state. You can see we're not uncertain. This is the probability. So 2/5 initial probability distribution, 2/5 for the first state, and then what would you think would be the probability that what's the second state? That white will be drawn on the second draw. It's the same thing as the probability that white would be drawn on the first draw, given our initial knowledge. 3/5. If we don't know what happens on the first draw, the probability that white is drawn on the second draw is going to be the same as the probability that white is drawn on the first draw. If we don't know what happens on the first 2 draws, then the probability that white is drawn on the third draw is exactly the same as the probability that white would be drawn on the first draw, and so forth, just like we did before. So it's going to be 3/5, because there are 3 white balls and 5 total balls. Right, so probability that white is drawn on the second draw, but only given our initial knowledge, is 3 over 5, using same arguments as above. Same mathematical arguments. If we do these same steps, we will find you will get 3/5. So now we have the probabilities. So our initial probabilities are 2/5, 3/5. Now we need a message. Let's suppose the message is that red, well, let's just keep our notation. R1 is the message. A red ball was drawn on the first draw. Now, what probabilities do we attach to the states? Now, after knowing that red was drawn on the first draw, what's the probability that red will be drawn on the second draw? Remember the states. These are the states. So what's the probability that red will be drawn on the second draw after getting this message? Well, there's 4 left, right? One of them is red, so a fourth. What's the probability that white will be drawn on the second draw, knowing that red was drawn on the first draw? There's 4 left. 3 of them are white. Notice the probabilities always have to sum to 1. Always. So, here's our initial probabilities. Here are our initial probabilities. Here are our probabilities after receiving the message. And the question is, we just need to calculate the uncertainty. The uncertainty initially would be, if we be negative 1 over ln 2 times 2/5 ln 2/5 plus 3/5 ln 3/5 using the uncertainty formula from lecture notes. And this is equal to approximately 0.4 times ln 0.4 plus 0.6 times ln 0.6, and then divide that by negative ln 2. And we've done this already. Actually, we did this, the 0.4, 0.6, 2/5, 3/5, same thing, 0.4, 0.6. We did that earlier. We get 0.97 if we round to the nearest 2 decimal places. And then our uncertainty after receiving the message would be negative 1 over ln 2 times, now we're going to have 1/4 ln 1/4 plus 3/4 ln 3/4, and that will give us, so 0.25 times the natural logarithm of 0.25 plus 0.75 times the natural logarithm of 0.75 gives us that, and we divide that by negative natural logarithm of 2, and we're going to get 0.81. So uncertainty decreased, and therefore the information content of the message. Since uncertainty decreased, we are in this case right here. So there is information in that message. Telling us that red was drawn on the first draw does give us information regarding which state, which color, the ball that will be drawn on the second draw, which is our variable that we care about, right? So we're going to do UPI minus UPA over UPI. So this would be equal to 0.97 minus 0.81 over 0.97, or approximately 0.165. And it's good practice that you convert that to a percentage, so 16.5%. The message contains 16.5% information relative to the maximum amount it could have contained. Now let's continue with this example, and let's suppose the variable of interest is the color that will be drawn, color of the ball that will be drawn on the third draw. And suppose the knowledge she has initially is the knowledge she had before. Right. And so our initial probabilities. So the state set, let's do the state set, I guess. Let's keep this in order here. Here the state set is either red could be drawn on the third draw or white could be drawn on the third draw. And the knowledge she possesses initially is what she had before, plus the fact that red was drawn on the first draw. So she knows that. She got that first message. She has her initial knowledge, and suppose she also has that, plus she knows what the color of the ball that was drawn on the first draw. And the question is, the variable of interest J is the color of the ball that will be drawn on the third draw. So again, there are two possible states. She knows that red was drawn on the first draw, but she doesn't know what was drawn on the second draw. So from her perspective, red could either be drawn on the third draw or white could be drawn on the third draw. And the probabilities, it'd be the probability that red could be drawn on the third draw given our initial knowledge, which is this right here. Hold on just a sec. Let me make sure that I'm telling you this right. Yeah. All right. Yeah. This is right. So the probability that red will be drawn on the third draw, given our initial knowledge, we can do the same thing we did before. You might think, okay, she knows that there was a red drawn on the first draw, but she doesn't know what happened on the second draw. So if a red was drawn on the second draw, then on the third draw, there's a 0% chance that a red will be drawn. If a white was drawn on the second, because there wouldn't be any red balls left. If a white was drawn on the second draw, right, then there are 3 balls left. One is white, one is red, 2 are white. There'd be a 1/3 chance that a red would be drawn. But remember that we said that logic was faulty, right? You want to use the product rule for probabilities. You want to do this. Do this analysis right here. If you do this again, you're going to find that the probability that red will be drawn on the third draw, given our initial knowledge, right? And our initial knowledge is the same as it was before, plus we know what was drawn on the first draw. And the probability that red will be drawn on the third draw is equal to the probability that red will be drawn on the second draw. It's the same thing, using the same logic as before. And the probability that red will be drawn on the second draw, well, there's 4 balls left. 1 of them is red, 3 of them are white. We know a red was drawn on the first draw. So 1/4, and then the probability that white will be drawn on the third draw is the same thing as the probability that white will be drawn on the second draw, using the same logic, which is 3/4. So our initial probability distribution, 1/4, 3/4. All right. And then we give her a message. So the message is R2. In other words, red was drawn on the second draw as well. And what are our probabilities after receiving the message? Now what do we think the probability that red will be drawn on the third draw is? Well, if red was drawn on the first 2 draws, we know red was drawn on the first draw. That was part of our initial knowledge. But we got a message that told us that red was also drawn on the second draw. Well, there were only 2 red balls of the 5. So the probability that red will be drawn on the third draw, 0. What's the probability that white will be drawn on the third draw? 1. And then I'll ask you, of all the messages we could have gotten, wouldn't you think this one gives us the most information? The most information in regards to what color of ball will be drawn on the third draw. Yes, this message gives us the most information, right? Because it tells us after having that message, we know exactly what's going to happen on the third draw. You can't get a better message than that. So what we should find then is that the information content of this message is 100%. Right? So UPI is it's with the 1/4, 3/4, right? It's the same thing. We calculated the 1/4, 3/4 one. It's 0.81. We did that up here. And then UPA we can calculate. It's -1 over natural logarithm of 2 times, and then one of the probabilities is 0, so 0 times log 0 plus, and then 1 times log 1. Now, something to point out, 0 times log 0. If you if you look at the logarithm function, which we've done already, but I'm going to do it again. It's like this. Here's 1. The natural logarithm of 1 is equal to 0. But natural logarithm of 0 isn't defined, right? What happens is this actually asymptotically approaches the vertical axis but never touches it. So there is no natural logarithm of 0. When x is equal to 0, natural logarithm is not defined. But what we can say is as x approaches 0, the natural logarithm of 0 approaches negative infinity, right? And so when we look at 0 times log 0, so you can't put log 0 into your calculator. It's not defined. The question is, how do you know what 0 times log 0 is? Is it 0? Well, here we know that as x approaches 0, this is 0, right? And as x approaches 0, this goes to negative infinity. So the question is, which one of these things approach faster? We'll tell you what the product of these is. If x approaches 0 faster than natural logarithm of x then the natural logarithm of x approaches negative infinity, then this will equal 0. But if the natural logarithm of x approaches negative infinity faster as x approaches 0, then x approaches 0, then this would be equal to negative infinity. So you can use something called L'Hopital's rule from calculus to figure out what this limit is. In other words, we want to find the limit as x approaches 0 of x times log x. Right? You can use L'Hopital's rule, and what you'll find is, indeed, as x approaches 0 faster than the natural logarithm of x approaches negative infinity. So this wins out right here, and it does equal 0. So I'll save you all the calculus. But you always have to do that whenever you have, these are called limits of indeterminate form. You don't know which one wins out. You have to use some technique in calculus to figure out what the limit is. So the point is 0 times log 0 is just 0. All right. So that means we have negative 1 over ln 2. Then we just have 1 times ln 1. But remember, ln of 1 is 0. And 0 times 1 is 0. And 0 over ln 2 is 0. So everything, your uncertainty after receiving the message is 0. There is no uncertainty regarding what ball will be drawn on the third draw. And it makes sense. You know exactly it's going to be a white one drawn on the third draw because you know that a red one was drawn on the first 2 draws. Your initial knowledge said a red was drawn on the first draw, and then the message that you got told you that red was also drawn on the second draw, so your uncertainty after receiving that message is 0. So the information content of the message, we know uncertainty decreased, obviously. So we just do this minus this over this. And that it's what? 0.81 minus 0 over 0.81. 1. 100%. You can't get a better message than that message. So hopefully this makes sense to you guys. Now we have 53 minutes, 42 seconds left. I said I was going to do 3 examples, but the video is already getting long enough, and I believe I will stop it there. So this concludes the video on information.